Okay, this is the sound unit notes. With this unit, the learning goals, I want you to understand the properties of sound. I want you to explain how beats are formed, which, if you remember, we've already kind of covered that. I want you to be able to explain the standing wave model for strings and pipes, which we've kind of already covered that. And I want you to explain the Doppler effect, which we also kind of covered that. So hopefully my goal for this unit will be talking about sound in a little more detail, and then a little more review of some of the other things that we've already discussed in our previous mechanical waves unit. All right, to get started then, sound. As we've talked before, sound is a mechanical wave, which means it needs a medium. Now, this medium can be a gas, liquid, or a solid, and the medium influences the speed of sound. So here we see a table, and kind of commits the sin here. It uses temperatures in Fahrenheit, but it gives us the velocity of sound through different mediums. And notice that as we go from 32 to 68 degrees Fahrenheit, the speed goes from 1,087 feet per second to 1,127 feet per second. Also notice that as we go down, we then get into some solids, some liquids, and just, take a look at some of these velocities. Sound travels the fastest through steel, warm steel, in fact. Also, hydrogen. Hydrogen's a gas, and yet it travels incredibly fast through a gas. That's because the molecules of hydrogen have very little mass, so it's easy to accelerate them. So as the sound wave travels through hydrogen gas, it can pass through the hydrogen gas faster because the particles are easier to accelerate. Over here we get another chart. This one's in meters per second. You'll see these two numbers over and over again. I think when I write problems, I like to say that the speed of sound through air is 345 meters per second. So that's just a pretty common numbers right there. All right, so what affects the speed of sound? Well, we have temperature and mass of the particles. So as temperature goes up, so does the velocity of the speed of sound. As the mass of the particles go down, the speed of sound increases. The next thing I want to talk with you about is diffraction, the bending of waves around corners or through openings. You may have observed this before. You're standing outside of a room, and yet you can hear people inside the room talking. That's because as waves go through an opening, they begin to spread out. This one really amplifies that. And first thing I want you to notice that this diffraction pattern depends upon the size of the opening. The smaller the opening, the more pronounced this pattern becomes. It also depends on wavelength. These are wavefront diagrams, so that's the wavelength. And notice that the wavelength, larger wavelengths, also make this a little more pronounced. And, with this diffraction, this is true for every wave, not just sound. Light diffracts, water waves diffract. It's just true for all of them. So let's say if I have a corner of a building, and I have a source of sound. That source of sound will bend around so that if there's another observer right here, they will be able to hear the sound from the source. So again, this is diffraction. There is some math with this. I might pull it up when we discuss these notes again in class, but I don't think you'll have to do a whole lot of calculating for this, just an understanding of what diffraction is. Okay, now, going on with characteristics of sound, we first have frequency. And basically, remember that frequency is cycles per second or oscillations per second. It's measured with a hertz, which is a 1 per second, or an inverse second. We classically break sound up into 3 different broad categories: 0 to 20 hertz, 20 to 20,000 hertz, and then 20,000 on up. So the 0 to 20 hertz, these are really, really low frequencies. And when it comes to sound, low frequencies, we observe it as a low pitch, so something really low. And this right here is what we call as infrasonic. We, as humans, cannot hear sound waves in this region. What we hear is in the audible. Hertz to right around 20,000 hertz. Now, this is an average. There are some humans that can hear below 20 hertz, and there's some humans who can hear above 20,000 hertz. But for the average of our species, 20 hertz to 20,000 hertz is what we can actually detect. And that's a pretty good range. If you're a musician, each frequency would be assigned a note or a pitch. So there's some really low sounding notes and there's some really high sounding notes. The 20,000 hertz and on up is called the ultrasonic. That you may have heard of, especially if you go somebody who's expecting. They may go and get an ultrasound to take a look at the baby. Ultrasound are really, really high frequency waves. We can't hear these. Some animals can hear them. I believe dolphins might be able to hear in some of this range. A lot of animals use this for echolocation. And what they do is they send out a sound wave. When the sound wave hits something, it's reflected. So with ultrasonic, because the frequency is so high, the wavelength is going to be really, really small. So when these really small wavelengths hit something and return, because the wavelengths are so small, we can get, the detector can get a very, very detailed picture of what's going on. So, bats and whales and dolphins, they use ultrasonic location or it's called echolocation, but they use ultrasonic waves and they send out waves, sound waves, that will reflect off of the ocean floor, reflect off of insects, reflect off of other fish. And when it returns to the animal gets a good idea for what's out there. So it's kind of like using light. The way we see is through reflected light waves. As light reflects off of something and enters our eye, we get a detailed picture of what's around us. You can do the same thing with sound. A wave is a wave. So, even though we can't hear infrasonic and ultrasonic, they are still considered sound waves. They are a disturbance in a medium. Also, when the medium and temperature of the medium is constant, so these sound waves are still a disturbance in a medium. So when the temperature and the medium and the temperature are the constant, these sounds will travel at the same speed. So what that means is, if everything is held constant, infrasonic, audible, and ultrasonic will all travel at the same speed. So that means that the infrasonic would have a very, if we take a look at our equation for the speed of a wave, for very low frequencies, we must have a very long wavelength. And for very high frequencies, you must have a very short wavelength. And just talking about this before, animals that use echolocation, they have to use ultrasonic because the audible and infrasonic wavelengths are so long that the waves will kind of diffract around the object instead of reflecting off of it. Now with pitch, with us, with musicians and humans in general, pitch is the perceived highness or lowness of a sound. So we can think of pitch as being like a qualitative measurement of frequency. Now, talking about frequency, we talked about the perceived highness or lowness. Now we can talk about the intensity. And sound intensity is the rate at which energy flows through some unit of area. And really, what I'm talking about when I say intensity is volume. How loud or soft is a sound? And that really, it depends on a lot of things. First off, it depends on how far away you are from the sound. As you get farther and farther away from a source of sound, it becomes quieter and quieter. So another thing that it kind of depends on is, how much power did the source have? So here we have some examples. This right here is a speaker, and it's pumping out some sound, and the sound waves travel out spherically. So here's another example. So right here's the source. We can see as it travels out, the wavefronts travel out spherically until we get to the outer edge. So the way we calculate how intense a sound is, we use a capital I for intensity, it's going to be the power of the source. So how many watts does the source have divided by the area. So we can see here, let's say this is a 700 watt speaker. And then this right here, let's say this is where your ear would be if you had an ear this big, the area of your eardrum. So for a lot of our purposes then, since these sound waves are spherical, everything, let's take a look at this example right here, everything along this wave front would have the same intensity. So we have to figure out what exactly is the area. And this is like a shell. What is the area? So it's kind of like surface area. So what's the surface area of a sphere? Well, that's 4 pi r squared. So intensity is power divided by 4 pi r squared, where r is how far you are from the source of sound. So notice then that volume is an inverse square law. The intensity is proportional to 1 over the distance squared. And in that way, sound has a lot in common with gravity. Gravity is an inverse square law. It becomes weaker with 1 over the square of the distance. Now, if I were to make some graphs, the way I would represent volume or intensity on a graph would be amplitude. And that's because sound is a mechanical wave. Okay, now, threshold of hearing. This is the intensity where we can just barely hear the sound. That is 1.0 times 10 to the negative 12th. Now the units, it's tower over area, so the units would be watts per square meter. That is the threshold of hearing. Now, keep in mind, what this is doing is these are sound waves that are hitting your eardrum. So you got something hitting your eardrum. Eventually, you're going to reach a pain level. So now we have the threshold of pain. This is 1.0 watts per square meter. So there is a lot. And really what sound is like the amplitude would be pressure, so changes in air pressure, atmospheric pressure. So just as frequency determines pitch, intensity determines loudness or volume. Volume, however, is not directly proportional to the intensity, our perception of volume. A sound that is twice as intense is not perceived to be twice as loud. And this is simply because the sensation, the sensation of loudness, how we perceive loudness, is approximately logarithmic. So when we calculate how loud a sound is, which is intensity, and when we calculate how much we feel sound is, we have to use something called relative intensity, where we're going to relate the intensity back. And this is where we get something called decibels. So the decibel level is a relative intensity. And the reason why we do relative is because it's easier to measure. The way we find the decibel level is by comparing the sound's intensity to the threshold of hearing's intensity. So the way we calculate decibels, so the volume, which is measured in decibels, we use a lowercase d, a capital B for that. That equals the number 10 times log of that sound's intensity divided by 1.0 times 10 to the negative 12th watts per square meter. And that is how we calculate decibel levels. And you can get a decibel meter for your phone. I've got one on mine. They're all cheap, and most of them are free, in fact. All right, so because this is logs, a difference in 10 decibels means that a sound is approximately twice as loud. So we can think of it as the volume doubles each time the decibel level increases by 10. So sounds at the threshold of pain will be 4,096 times louder than sounds at the threshold of hearing. So this chart right here gives us some different sounds and their decibels. So notice that the threshold of hearing would have it's 1 times 10 to the negative 12th. So its decibel level is 0. And there's a reason for that. Log, there's some properties of log. So log of, let's say, some number x divided by x, in other words, log of 1 equals 0. So that's one property of log. A jet plane, or first off, the threshold of pain. Well, looking at this, this table says that it's right around 3 watts per square meter. It's close, but it's right around 125 decibels. So at 125 decibels, that's when you really start to experience some pain. Okay, so since we're dealing with logs, we can do some log math. So just as a refresher, let's say you have y equals log to the x. Then x would equal 10 raised to the y. Another thing, if you have log of x divided by y, which if you look at our model, we do. Our model is like an x over a y. Then this would equal log of x minus log of y. So that's a handy one. There's also a log of x times y. That would equal log of x plus log of y. Okay, now finally, there's an upper limit. You will never hear a sound greater than 190 decibels. Remember that sound is a pressure wave. It's pushing atoms together. And at 190 decibels, the air molecules are pressed so close together that the sound cannot physically travel through them anymore. So think of all the atoms and molecules stacking up on each other. So at 190 decibels, that is the loudest sound anything can ever achieve. All right, that concludes this unit's first video.